If I draw a picture of a cliff like this, a ball rolling off the edge of the cliff, let's say at a velocity of 10 meters per second, on a cliff that, let's say, is 20 meters high, we know that that ball will follow a path that we call, what's the shape of that? It's a parabola, right? We call it a parabola. It's described by the equation for the y component, d is equal to vit plus 1 half et squared, which really is y is equal to ax squared plus bx plus c, the equation for a parabola. We would describe this by breaking it down into x and y components. V is equal to delta d over delta t for the x component, and we would say d is equal to vit plus 1 half at squared for the y component. Every single time, right? Every single time. Now, today, we're going to learn to solve problems where we're launching the ball from ground level at an angle like this, and let's say 10 meters per second, and let's say at an angle of 30 degrees. The path followed by that ball will also be a parabola, although it'll be a full parabola this time instead of just a half parabola. And we will also describe this by using the same two equations. V is equal to delta d over delta t, and we've got d is equal to vit plus 1 half at squared. Now, there are differences, but you can see that we always, no matter what, start off the same way. When you see question number 1 on your final exam in January, you will start off like this, for sure, 100%. You need to start off by drawing the picture. You need to start off by labeling this equation for the x component and this equation for the y component, regardless of whether the ball goes off the edge of a cliff or whether it's kicked from ground level and then comes back down to ground level. There are, however, differences. What's the fundamental difference between problem number 1 and problem number 2? What's the biggest difference between them? Like, not necessarily in terms of how we're going to tackle it, but just the biggest difference in terms of what you see. Yes, we have a funny angle in the second one that we don't have in the first one. So, what do we got to do with that then? We got to get rid of the funny angle, so we take it off to the side. Here's our 10 meters per second. Here's our 30 degrees. We label this x. We label this y. We find the x component by using some trigonometry that we did back with our relative motion navigation problems, back with our vector addition problems. Cosine 30 degrees is equal to x over 10. X ends up being equal to 8.66. Sine 30 degrees is equal to y over 10. Y equals 5.00. Look, these problems are the same in many ways, including the fact that the horizontal velocity remains constant. Including the fact that the vertical velocity increases as you go down, although in this case it actually decreases and then increases as it goes back down. They're the same in many ways, but they're different in the sense that the x velocity in the first question is 10 meters per second. The x velocity in the second question isn't 10 meters per second, it's 8.66 meters per second. So the first difference, the number that's given to you versus the number that we have to find by taking an x component, because we got a funny angle. Delta d we don't know here, right? Delta t we don't know. That's okay. Delta d we don't know here. Delta t we don't know. So this is the same. What's delta d for the y component over here on the left-hand side? Problem number 1. Yep. No. Delta d for problem number 1. The displacement vertical. Almost. So close. Not 20, but negative 20, yeah. What do you think the vertical displacement would be over here? What's the change in position for the displacement or for the ball in problem number 2? Well, it's a good one, yeah. 0, good, good. Why is it 0, Maddie? Good, good, because it ends up on the ground. It ends up where it started from. So we're going to say that's the second difference. A lot of similarities, right? But two differences so far. One, the horizontal velocity is 10. The horizontal velocity is, well, the x component of 10, which is 8.66. The vertical displacement is negative 20. The vertical displacement here, because we end up on the same level, is 0. So negative 20 is equal to VIT. What's VI over here? That is for the vertical component, right? For the horizontal component, it's 10 meters per second. But for up and down, how fast is it moving initially? Rachel? 0. And we don't know what the time is, but it doesn't really matter because 0 times time is 0, right? What would be the initial vertical velocity rate here? How much of that 10 meters per second is y component? We know this, yeah? 5 meters per second times the time. That's the third and final difference. The third and final difference. 0 initial y velocity for problem number 1. The y component of 10 initial y velocity for problem number 2, or 5.00 meters per second. Everything else is the same. So let's plug in the rest of our stuff here. Let's add that to 1/2 of negative 9.81 times t squared. Now we've got t in two places in the second equation over here, but it's only one variable. It's only one unknown. It's tricky to solve for, though. Let's try this. Let's divide everything by t. What's 0 divided by t? What's 0 divided by anything? 0. What's 5t divided by t? 5. T divided by t is 1, right? So 5t divided by t is 5. Half times negative 9.81 is negative 4.905. What's t squared divided by t? T squared divided by t. X squared divided by x. T, yeah, it's t. Good. Make sense? T squared divided by t is t. So we've simplified 0 equals 5t plus half times negative 9.81 times t squared into 0 is equal to 5 minus 4.905t. Let's take the 5 over by subtracting. And then let's say 5 divided by negative 4.905. We end up getting negative 1.019. Which we turn around and sub back into there, and we multiply by 8.66 to get the horizontal displacement. So mathematically, it's a little bit different, right? Mathematically, it ends up being a little bit tougher to solve for the value of t because VI isn't 0. But fundamentally, it comes down to the same thing with the exception of these three things that are circled. We set it up exactly the same way, but we make V whatever number is given to us. We make V whatever number is the horizontal component of the number given to us. Here we make delta D the negative of whatever number is given to us. Here we make it 0. And finally, we make VI for the y component 0, and we make VI for the y component, well, the y component of whatever number is given to us. And then we just solve. Okay? Mathematically, one might be easier than the other, but if you're good at math, we'll be able to solve it either way, as long as we get our differences between those two problems. Question number 1 on your final exam will be one of these two questions that you see up on the board, with different numbers, of course, and some different context or whatever, but it's going to boil down to one of these two questions that we see up on the board. Does that make sense what the difference is? Okay, I want to do an example, like a real example from start to finish, not comparing, but just a problem that's launched at an angle up like this from start to finish here. So as baseball players often practice their swings in a batting cage in which the pitching machine delivers the ball. The baseball is launched with an initial velocity of 22 meters per second at 30 degrees, and the player hits the same height from which it was launched. How long is the baseball in the air on its way to the batter? So the baseball is launched like this, not from ground level, but from the level at which it's hit. So it's like from ground level to ground level. What do you want to do first, besides the diagram that I just drew? Yeah, let's deal with the funny angle. We don't like it, let's get rid of it. Okay? Listen, that's the moral of the story in physics class. Hey, you don't like something, get rid of it. Just deal with it and get rid of it. Here's our 22 meters per second at 30 degrees. Let's draw a little triangle around it. This isn't new, right? And using it in this context is new, but finding the x and y components isn't new at all. Cosine 30 degrees is equal to x over 22, adjacent over 22. Or if you're one of those sine law people, whatever it is that you do, should get the same answer. 22 cosine 30. I get 19.0526. We're going to say sine 30 degrees is equal to opposite over hypotenuse. That's going to be exactly 11 meters per second. You know what I love about these questions? These projectile motion questions? First of all, they're so concrete. Okay, that's what I like most about them. It's like, this is like the most concrete thing that we can do in physics almost, right? Kick a football, where's it going to land? Okay, predict where it's going to land. But one of the things I like about these questions, beyond that, beyond the concreteness, is that, look, for the first time, we're really seeing how skills that we've learned earlier on can be applied in a completely different context, right? We learned our vector analysis skills, our funny angle skills, back when we were adding displacement vectors together, and here we are in a completely different context, but we're really doing the same thing. All right, let's break this up into x and y. We're going to say, what is it for x component again? Abby, what is it for x component? Good. V equals d over t because it's constant velocity, right? And what is it, Sydney, for the y component? Yeah. Good. And listen, if you don't remember that whole equation, that's okay, right? It's on your data sheet. Just be familiar enough with it that you can look on your data sheet and find it, right? Sub in some numbers. Do we know what v is for the x component? Braden, do we know what v is? Horizontal velocity of this is? Yeah, not 22, is it? What is it? 19.0526, good. We don't know what d is. All right, that's okay. Do we know what t is? No, we don't. That's okay. No big deal. Let's go over here to the y component. The displacement for the y component is, Adam, what's the displacement for the y component? Where does it end vertically relative to where it started?
It should be in the same place.
Yeah, so in other words, the displacement is 0, right? So let's sub that in as 0 equals VI for the y component. VI because the speed changes, right? But initially it's what? Taylor? No. It was 0 when it was launched horizontally, right? But how much of this 22 is y component?
11.
Sorry? Yeah, 11. Good. Does that make sense? Okay. Okay. So delta t plus 1/2 of neg 9.81 times t squared. Let's divide that by t. 0 divided by t is 0. Divide this by t. 11 divided by t is, 11t divided by t is 11. Half of negative 9.81 is negative 4.905. T squared divided by t is t. That looks a lot better, right? Divided everything by t. Take the 11 over by subtracting. And then let's say negative 11 divided by negative 4.905. 2.2426. That's all we're looking for, right? Is how long is the baseball in the air? So we're going to round that to, what, 3 digits, I think it is? Yep, 2.24 seconds. Now, having said that, if I wanted to solve for the horizontal displacement, I could turn around and sub it in there, right? If I was looking for delta D, x component, but I'm not. What's different about this question than the questions that we were working on Thursday and Friday last week? This, we had to find the x component of 22. This, we had to find the y component of 22. And this, which last week was whatever the height of the cliff was. Now it's just 0 because it lands on the ground. Then the algebra is a little bit different, right? Algebra is a little bit harder, actually. I'm done. All right. All right, let's have a look over the front. I want to take a look at question number 2 that you were assigned a few minutes ago. 2 on the second page of that worksheet. It says a golfer is teeing off on a 170-meter long par 3 hole. The ball leaves with a velocity of 40 meters per second at an angle of 50 degrees. We want to know how far from the flagstick is the ball when it strikes the green. Most people recognize this part of it, which is great. The fact that the 170 meters is not really relevant, at least at the start of this question, right? The 170 meters is where the hole is, but it doesn't say that's how far the ball goes. We don't want the information, at least right away, about where the hole is. We just need information about the ball. And the 170 meters has nothing to do with the ball, at least not right away. Let's draw a picture here and label what we do have. We know that we have a ball that follows a parabola. We know that it goes off at 40 meters per second at an angle of 50 degrees. And we want to find out, well, really, we want to find out this distance right here, the horizontal displacement. We know the ball, or the hole, is way down here, which is 170 meters away from where the ball was hit. But really, in order to find out how far away from the hole you are, you got to find out how far the ball goes. So let's go off to the side here, do the x and y components, and then we'll do our thing here. This is 40 meters per second. This is 30 degrees. We're going to say cosine 30 is equal to 40 cosine 30 is equal to x over 40. So we're going to say 40 cosine 30 gives me 34.641. And the y component, we're going to say sine 30 degrees is equal to opposite over 40, which is going to equal 20 meters per second. So now we do our x and y components. We're going to say x, v is equal to d over t. The x component of the velocity is what? Ireland, what's the x component of the velocity? 40, 34, or 20? Good. 34.641 meters per second. The displacement we do not know. It's not 170, unless we get lucky, unless we get a hole in one, and the ball goes right to the pin. The time we also don't know. But we do know that the y component can be represented by this equation, VIT plus 1/2 AT squared. Tell me, Kyle, what's the y component of the displacement here? Like the ball starts on ground, the ball ends where? Nope. The y component of the displacement. Displacement. Yep.
It's 50 degrees, not 30.
Oh, are you kidding me? 50 degrees. So these are all wrong then, eh?
Yeah.
All right. Let's try that again then. So we're going to say 40 cos 50. 25.7115. Thanks for pointing that out, by the way, guys. Like a while later on. Thanks for pointing it out at all. But to the rest of you, can you sense my sarcasm? Thanks for pointing it out earlier on. The y component, by the way, is 40 sine 50. 40 sine 50 is 30.6418. So now we're going to say x is 25.7115. Now I think we're back on track here. The y displacement is what? Kyle, what's the y displacement? Where does it start versus where does it end? On the y-axis. You know this. Come on, you know this. Look at it. Starts here, goes up. I don't care where it goes this way, but it goes up, and then it goes back down. What's the vertical displacement?
25.
No.
30.
Where does it end vertically relative to where it starts? Brogan, help him out. 0. Because it starts on ground level, ends on ground level, right? Does that make sense? I knew you knew that. I told you knew that. Right? Trust me, when I say you know this, right? 0. Good. VI for the y component is 30.6418 times delta t plus 1/2 of -9.81 times t squared. Now, some of you are still having a little bit of trouble rearranging this. Let's divide everything by t. We can do that. We can divide it by anything we want, but t makes sense. 0 divided by t is 0. T divided by t is 1, so 30.6418. 1/2 times -9.81. T squared divided by t is, take the 30 over by subtracting, right? 30 goes over by subtracting. Divided by 4.905, because that's what's attached to the t, right? Take it over by dividing by that. 30.6418 divided by 4.905 equals 6.247 seconds. So take that, sub it into here to get the horizontal displacement, and I think it was like 161 or something, wasn't it? And then to find out how far away that is from the pin, I would say 170 minus 161, 9 meters away from the pin. Is that okay? Let me just do one follow-up question with that. Let's say we were asked for how high this ball ends up going. Like, what's the maximum height? You can see the ball. You can see the ball going up in a parabola. At this point right here, its maximum height, how high is that? A couple ways to tackle this. One way that's easier than the other. Anyone? Brogan, you were working on that on your assignment, right? Did you figure it out? No? Rachel, you got that one? Okay, you could. So what do you mean, though, exactly? You cut it in half. So you'd what? Okay, so you cut it in half, but like, how would you cut it in half exactly? Okay, you could. Yeah, you could. I couldn't because I don't know how to use it, but you guys are good at graphing calculators, right? You could do that. Here's what I'd do. You could cut it in half. That's not what I do, but you could cut it in half. Say 6.24 seconds took the whole trip, right? Half the trip is 3.12 seconds. And then sub that into d is equal to VIT plus 1/2 AT squared and solve for d. What's the displacement at half the time? Here's the easiest way to do it, though, I'd say. For the max height, let's say VF squared equals VI squared plus 2AD. This one's valid, right? Because anytime we have acceleration, I had to use that equation. When the ball goes up like this, horizontal speed remains the same, right? What happens to the vertical speed? What happens to the vertical speed right here? Up and down right here? 0. So we're going to say that's 0. VI is 30.6418. A is negative 9.81. Solve for the displacement when VF is 0. Solve for the displacement when it stops. Why? Because it stops at its maximum height. VF squared minus VI squared, taking over what's not attached to the D. Divide by 2A because that's what is attached to the D. And we sub in those numbers. 0 squared minus VI squared. What was it? 30.6418. Let's see what we get here. Zero squared minus 30.6418 squared divided by 2 times negative 9.81. 47.9 meters.